Okay, thanks for the introduction. So hi everyone, my name is Youchen Sun and I'm a PhD student from the Nanyang Technological University. And I'm very excited to present our work on behalf of my co-authors Sun Zhu, Sha Xiao, Zhang Jie, and Ong Yusong. And the title of our work is Disentangling Motives Behind Item Consumption and Social Connection for Mutually Enhanced Joint Prediction. So this is the overview of today's presentation. So I'll start by introducing the background of the social recommender system, which is related to our work because essentially our model is a social recommender, except that we have a auxiliary social link prediction task. So normally on a social media or a social platform, the user can either consume items, so which is of the main interest in the recommender system, or they can connect with other users. So the conventional recommenders, they mainly like collaborative filtering, they mainly leverage the user item interactions for the user modeling. But social network, the social recommender system, they further use the social network to boost the prediction performance. So the main theory behind is called the social influence theory, which states that people are more likely to be influenced by the people they know. So the existing work can be categorized into three types. The regularization-based method just add a regularization term to the objective function to force the connected user to be close in the embedding space. And the cofactorization-based method, they conduct the matrix factorization on both the user item interaction matrix and the social network adjacency matrix. And the ensemble-based method just aggregate the neighborhood information into the user's representation. And recently, graph neural networks such as RecSys or graph attention network, they are used in recommender system and also social recommender system because they are powerful in modeling the intricate relationship and the information diffusion within the network. For example, in the social network, with the GN, we can not only learn the influence of the direct neighborhood, but also the influence from the neighbor from multi-hop. So despite of their effectiveness, we have identified several limitations of existing social recommenders. So the first one is most of them, they model the user consumption and the social connection independently. For example, in social recommenders, most work, they just use the social link to boost the item prediction performance. Or on the other way around, some work in the social link prediction, they use the user's consumption information to help enhance the link prediction performance. But very few of them, they consider jointly modeling those two behaviors simultaneously. But actually, they are highly intercorrelated. And it can be supported by these two theory, the one theory already mentioned in the previous slide, the social influence theory, and also the homophily theory, which states that individuals they are with similar characteristic more tend to build social connections. And some recent work, they found out that if the joint modeling those two behavior, it will lead to better performance for each task. And the second motivation is that actually users' motives to consume items or to build social relations are multifaceted. So take this toy as an example. If the user wants to watch a movie, he might have multiple intentions. He might want to watch a movie with his family, or he might want to kill time or gain some knowledge. So his preference under those different intentions can be different. And similarly, in the social network, the user might connect with other users for different reasons. It could be his colleague or alumni, so his characteristics under different relations are also different. But existing work, most of them, they learn a single embedding for the user, which means that such semantics are highly entangled in the user representation, which will lead to suboptimal user representation. So this is at the each network, at the level of each network alone. And further on this, we also consider that if we want to model the mutual influence between those two networks, we actually can also discriminate that mutual influence at this facet-to-facet level. So still take this movie watching as an example. So this user, maybe when he wants to pick a movie to watch with his family, he might want to ask his friends for advice. But when he wants to pick a movie to say gain some knowledge, he might ask a colleague at work. So this suggests that different social relationships can have different extent of influence for the user's consumption intention, consumption preference under different intentions. So to address the aforementioned challenges, we propose a method called disentangling motives behind item consumption and social connection for mutually enhanced joint prediction, short for DMGP. So the main contribution, first one is we propose a multitask learning framework. So we perform both item prediction and the social link prediction and optimize them jointly. And the second contribution is we learn the disentangled representation in each network corresponding to the consumption intention and the social relations. And finally, we model the mutual influence between the two networks at this facet-to-facet level. And this is the overall framework of our proposed method, which consists of 4 modules. The interaction disentangling layer and the social disentangling layer are used to learn the disentangled embedding in each network. And after the disentanglement, they are passed to the mutual refinement model to perform the mutual refinement between the embedding. And finally, we have the prediction layer, which perform both the item prediction and the social link prediction, and for a joint optimization. And for the network disentangling module, here I put an example of the interaction network disentangling, and the design for the social network disentangling is similar. So here we use this neighborhood routing mechanism, which essentially each user is initialized with P chunks of initial embedding, and each of them corresponding to a intention facet. And then we use this routing mechanism to iteratively aggregate the neighborhood information on each facet based on the attention score. So this attention score just means how likely is this connection attributed to this current facet. And we repeat this several times until the convergence. And we also add an independence regularization to the learned embeddings to ensure that the representation of each facet does not contain repeated information. And then for the mutual refinement module, it is used to discriminate the mutual impact between the two networks at the facet-to-facet level, and then they are used for the mutual refinement. So it is actually embedded in the social disentangling layer. So after we learn the disentangled embedding in each layer, we will perform this mutual refinement. So on the screen is the example of how the social embedding is used to refine the user's preference embedding. So basically, UIP means the user's preference embedding on facet P, and then we aggregate the user's social embedding on all the Q facets. And we learn the attention score, alpha PQ, which means how important is the social facet Q on refining the intention facet P. And then we do the linear combination to aggregate all the embeddings. And for the other direction, which is to use the item embedding to refine the social embedding, it follows the same design, but except that the mutual influence is actually asymmetric, which means that the influence of intention P on relation Q does not equal the influence of relation Q on intention P. So we use another set of parameter for the other direction of refinement. And finally, have the prediction layer, which since now we have Q embeddings for the social space and P embeddings for the intention space, so we do the inner product and sum over all the facets and for the final prediction. And for the model optimization, we choose the Bayesian pairwise ranking loss for the 2 tasks, one for the item prediction and one for the social link prediction. And we use the gamma as the balancing parameter. And we also have the independence regularization and the L2 normalization, regularization. For the experiment, we ran it on 3 datasets, Opinion, Chell, and Last.fm, which both contains the social network and users' interaction information. And following the convention of previous work, we convert the ratings into the implicit binary feedback, and we also filter out users with fewer interactions and social neighbors. And we use the hit ratio and NDCG to evaluate the performance of the model. So here's the performance. Here's the overall performance of our model on the 2 tasks. item prediction task and the social link prediction task. So we compare mainly with two types of baselines. So the first type is the three joint methods that also perform the item prediction, social link prediction simultaneously, and the other classes are the ones that do the single task. So as we can see, our method outperform the baselines consistently on all the three data sets and also on both tasks. We also did an application study to see the effect of the joint modeling. So basically, for item prediction, we do not optimize the social link prediction. So we remove the loss from the objective function, and for the social link prediction, vice versa. And the result also shows that the benefits of jointly modeling those two behaviors. And then here I show some of the component study of our framework. So on the left is a visualization of the attention score of this user with its social neighborhood as well as its item neighborhood. So this score just means how likely are they connected, or the item consumption is attributed to this facet. So as you can see, the probability distribution is different across different facets. And on the right, we also investigate the number of the intention facet or the relation facet. How does that affect the performance of our model? So as we include the facet number, initially the performance increases, and as we further increase it, the performance starts to drop. And as for the component study for the mutual refinement module, we have DMGP. So we first degraded by changing the asymmetric mutual influence to the symmetric mutual influence. And then we further degraded by replacing the attention model with the mean pooling module. And finally, we completely removed the mutual refinement model. And in the table, as we further degrade our model, the performance drops gradually, so which indicates the effect of the mutual refinement, symmetric mutual refinement design. And finally, on the right, another case study to visualize the attention score we learned for the mutual influence. So alpha PQ on the top is how the different facet Q influence different intention facet P, and on the bottom is how the different intention facet P influence the relation facet Q. So you can see the distribution is not uniform and is also not symmetric. So to recap, we propose a method that a joint framework that perform both item prediction and the social link prediction. And we conduct the latent motive disentanglement corresponding to the consumption intention and the social relations in these two networks. And we differentiate the mutual influence at the facet-to-facet level. And in the future work, we would like to explore the interpretability of the disentangled representation, possibly with the help of like the review information or other semantic labels. We could also explore how this disentangling can help with a more reliable, explainable social recommender system. So that's all for my presentation, and thank you for your attention.
Thank you, Luciano, for the presentation. Very nice. If there is any question from the audience, you can come to the microphone here. Okay, I have a question here from Slido. What do you think is the limitation and potential improvement regarding the disentangling approach used in your work?
Okay. As I said before, because in this model, we are learning the latent representation corresponding to the different motifs, because we don't have the specific label that indicate the relations or the consumption intentions. So it's latent at the moment. So as I mentioned in the future work, improvement is to maybe leverage the other data to see if the disentangled representation can have some actual meanings.
Okay, thank you. Is there any other questions? I don't think so. I have a quick one. I was thinking about the data set you have used in the evaluation. do this data set have the motives you were talking about in your data model, or they don't?
No, it's just the social link, no
Okay.
motives.
And how do you think to handle this kind of information that is missing?
Because I learned the latent representation, so
Okay,
it actually...
it was latent.
Yes.
Okay, thank you so much.
Thank you.
Any other questions? No? Thank you, Yu Chen, for the presentation again.